Okay, this is how and why a charged particle moving inside a magnetic field experiences a magnetic force. If charged particle is moving inside a magnetic field at some angle different than parallel, so this charged particle will experience a magnetic force depending on QVB, which is the charge and the magnetic field and the velocity, and of course angle between the velocity and magnetic field. Right. So this is the this is the equation QVB sine theta. But if you put a wire inside a magnetic field, this wire also experiences a magnetic force if it carries some electric current. Electric current is motion of electric charges. In here, a single charge is moving inside the magnetic field, but in here, thousands of charges, maybe billions of charges are moving inside the magnetic field. Because electric current is motion of thousands of charges moving through the wire. So while these charges are moving in this wire, with some speed, of course this charge must experience a magnetic force just like a single charge. And equation between the magnetic force acting on a single charge and equation between the magnetic force acting on a current carrying wire are very similar. In fact, we can get this equation from that one. When I was talking about the 12th grade, 11th grade titles, I give the definition of the electric current, and I gave you an equation about the electric current. It was like this. I is equal to delta Q divided by delta T. Delta Q is how much charge is passing through the wire. Delta T is in how many seconds it's passing. This is the delta Q over delta T is the I. If I cross product these two quantities, I can get delta Q. What is delta Q equal? I times delta T. Now you are going to write here, instead of Q, I times delta T. Right here, instead of Q, write I times delta T. So F is equal to I times delta T, which is Q, multiplied by V, which is the speed of the charge, multiplied by B, multiplied by sine theta. What is V times delta T calculate? Speed times time. It calculates distance. Distance to charge travels. Distance travels a charge, but the charge travels a distance is equal to length. Distance traveled by the charge is equal to length of the wire. Instead of V times delta T, what am I going to write? Length of the wire. Now we got the equation. Equation for magnetic force acting on a wire is I times L times B times sine theta. Yani BIL sine theta. This is the equation. BIL sine theta is the equation for calculating magnetic force acting on a charge. Q will be sine theta, changes to BIL sine theta. And why there is a charge force acting on a current carrying wire? Because charges are in motion inside the wire. Assume that electric current is moving from left to right. So this is the direction of electric current from left to right inside this wire. So we know that electric current direction is assumed to be the same direction of the motion of positive charges, right? If electric current is from left to right, so can you say that each positive charge moves from left to right? Yes, because electric current is considered to be in the same direction of the positive charge motion. So electric current is from left to right. That's why electric motion of the charges must be from left to right as well. Okay, so now let's find the magnetic force acting on this charge inside this magnetic field. The magnetic field is cross, which is into the page. So forefinger into the page. Thumb from left to right. Yes. Force acting on positive charges upward to the board. Yani each force experiences a small force in this direction. So these charged particles are moving inside the conductor. So when they are acting a force upward direction, they will push the wire upward direction. That's why wire will start moving upward to the up to the plane of the board. Yeah, and as these charges are moving, they will push this wire upward. And some of these forces acting on each charge, when we add them up, we will get the net force acting on the wire. So, current in a wire consists of many charged particles moving through this magnetic field, on each of which acts an individual magnetic field. Small f's, F, individual magnetic force acting on each charge. So when we edit them all, the force on each particle is transmitted to the bulk of the wire. Bulk means body. So this force will be transmitted to the body of the wire through the collisions of these electrons with other particles. And after that, we are going to add them. When we add them, a resultant force will act on the wire due to the sum. What does sum mean? Addition of them. We will add them all, and we will find a resultant force acting on the charged particle. Yeah, the origin of the magnetic force acting on a current carrying wire is the magnetic force acting on the charges which are moving inside the conductor. And of course, according to this equation, BIL sine theta, B is the magnetic field intensity. I is electric current, how much electric current passes through the wire. L is length of the conductor inside the wire. Theta is the angle between magnetic field lines and electric current direction. So in the first title, it was the angle between magnetic field lines and direction of the charge. Now, direction of the electric current. Direction of the charge changed to direction of electric current. So equation is same. And according to this theta, force can be maximum, can be zero, or can be half of maximum at some angles. At what angle sine theta is maximum? 90. If the electric current is perpendicular to the magnetic field lines, so angle between electric current and magnetic field is 90. So sine 90 is 1. Maximum magnetic force acts on the conductor, BIL, the same as the charged particle. If charged particle moves perpendicular to magnetic field lines, because angle between B and B is 90, it was maximum, again maximum. What if the wire is parallel to magnetic field lines and electric current is parallel? Two angles possible. Electric current direction and magnetic field direction can be in the same direction. So in this case, angle between them is 0. If electric current direction and magnetic field direction are opposite, angle between them is 180. So both are sine 0. So magnetic force, in this case, 0, same as the charged particle as well. At what angle magnetic force is half of the maximum? 30 degrees. In here also. If the angle between the wire and the magnetic field is 30 degrees, sine 30 is 1 over 2. That's why magnetic force will be half of the maximum magnetic force. Okay. And, of course, a force is a vector quantity. We have to, again, use right-hand rule. Same right-hand rule we will use. No different. For charged particle, forefinger was the magnetic field direction, again magnetic field direction. In charged particles, thumb was showing the direction of the charged particle motion. Now it will be direction of the electric current, because we know that electric current is the motion of the charged particles. So this time now, thumb will show electric current, not V, not VI. Because electric current is assumed to be motion of the positive charges, so palm will show the magnetic force direction. Why? Because opposite of the palm is direction of the force acting on negative. But electric current is defined as the motion of direction of the positive charges. Yeah, in this title, we have only power for magnetic force, not opposite of the power. B is the magnetic field direction. I is electric current direction. Palm is the magnetic force acting on the electric current acting on the wire. Now, we don't use this side in this title, only this side. And again, maybe you remember in the previous title, this magnetic force is perpendicular to, always perpendicular to magnetic field. Magnetic force, always perpendicular. Again. In the previous title, magnetic force was perpendicular to velocity, but velocity changed to I. So magnetic force is always perpendicular to electrical attraction. These two still possible. Angle between them is always 90 degrees. Yeah, the angle between magnetic force and magnetic field is 90 degrees. Angle between magnetic force and electric current is again 90 degrees. Just like the previous title. In the previous title, in the charge, angle between force and magnetic field was 90. But angle between magnetic force and velocity was 90 again. Well, instead of velocity, we put electric current direction. Okay? Same right-hand rule we are going to use. Now we are going to solve a problem. We will solve a problem. You will see it's not so hard. Now this is the problem. A 6-meter wire. 6-meter wire. It's the length of the wire. L. 6-meter wire. L is 6 meters. Carries a current of 7 ampere. So this is the length. This is the electric current, I. This electric current is towards the positive X direction. Which set we are going to use now? Positive X. X, Y, Z. Second set. X, Y, Z. Your coordinate system will be positive X, negative X. Positive Y, negative Y. Positive Z, negative Z. Okay, towards positive X direction, your electric current is 7 ampere in positive X direction. That's why I'm going to draw in here second set of directions. This is the second set of directions. Positive X to the right of your page. Negative X is to the left of your page. Positive Y to the top of your page. Negative Y is to the bottom of your page. And positive Z is out of your page. Negative Z is into your page. Okay. And a magnetic force, how much? 7 times 10 to the power negative 6 Newton. X on the wire in which direction? Negative Y. So magnetic force F acting on this wire is 7 times 10 to the power negative 6 Newton in negative Y direction. So electric current is in positive X direction, but magnetic force is in negative Y direction. Now I'm going to draw magnetic force vector in negative Y direction. Clear? Find the magnitude and direction of the magnetic field. B is the question now in this problem. Find direction and magnitude of the magnetic field. Alright, now I'm going to first find the direction. I will use my page again, but this time my set is not north, south, east, west. It will be positive X, negative X. Positive Y, negative Y. You have to drop this first. Without dropping this coordinate system, don't start solution. So positive Y is to the top of your page. Negative Y to the bottom of your page. Positive X to the right of your page. Negative X to the left of your page. Now, let's start. What is given in the problem? F and I. F is the force. If magnetic field is the question, show first by indicating direction of the magnetic force. In which direction is the magnetic force? Negative 5. Your palm force must show negative 5. Is this negative 5? So palm must show negative 5. First do this. Is that correct? My palm is showing negative 5? Yes. After that, current direction. My thumb is showing now out of the page, which is positive Z. But question says electric current is not in positive Z. It is in positive X. I will change it to positive X. Now my thumb is showing positive X direction. Yes. My palm is showing negative Y direction. Yes. Look at my forefinger. Out of the page, which is going to be
Negative Z.
out of the page, which is going to be positive Z. Into the page is negative Z. Out of the page is going to be positive Z directions. Okay? Let's do it again. If the magnetic field is a question, first you should start with the force. Magnetic force is in negative Y direction, so my palm will show negative Y direction. You see that? Negative Y direction. But now, next step, thumb. But my thumb is wrong now. My thumb is showing out of the page, which is positive Z. But question says variable. Question says it is in positive X direction. Now I am going to shift it to positive X. I did it. Positive X. Force is negative Y. Forefinger is out of the page. Out of the page indicates positive Z. And dot. I am going to draw it as dot, which will say you magnetic field is in positive Z direction. Positive Z direction. Yes. Now let's calculate the magnitude. Equation for calculating magnetic force on the wire is BIL. Now look at the angle between B and I. B is in vertical. I is in horizontal. What's the angle between a horizontal and vertical line? 90. This is why maximum magnetic force X on the wire BIL. Okay? I know how much F is, it's given. I know how much I is, it's given. How much L is given. What is the question? B. Simplify equation by dividing I and L. Divide both sides, I and L. Simplify I and L. So B is equal to F magnetic divided by I L. F magnetic is given as 7 times 10 to the power of negative 6. I is given as 7. L is given as 6. Don't forget to use the bracket if you are going to use a calculator. Magnitude of the magnetic field is 1.7 times 10 to the power negative 7 Tesla. But in which direction? You should write, put it at comma, in positive Z axis. So answer will be this way. First magnitude and add its direction after the magnitude. 1.7 times 10 to the power negative 7 Tesla in positive Z direction. Now we will continue another problem. Sample 5E. Sample 5E. A wire of 36 meter. A length is again given as 36 meter. Recorded. L is 36 meter. Long carries a current of 22 ampere. Electric current is, this is length. This is electric current I. But this time, electric current is from east to west. Third set. We are going to use third set. East, west, north, south, upward to the sky, downward to the ground. So, electric current is given 22 ampere to the west. From east to west means to the west. So, I'm going to draw the third set. To the right of the page is east, to the left of the page is west, to the top of the page is north, to the bottom of the page is south. And now let's indicate electric current direction first. Electric current is to the west. Let's draw the arrow to the west. Is it correct? Electric current is vector showing to the west?
Yes.
Yes. Continue. If magnetic force on the wire due to Earth's magnetic field is downward towards the Earth, downward to the ground, we represent it by cross, remember? Downward to the ground is cross. So magnetic force will be downward to the ground. So 4 times 10 to the power negative 2 Newton, downward to the ground, cross. I will represent it by cross, just like this. Magnetic force is downward to the ground, which is cross. Find the magnitude direction of the magnetic field. Again, P is the question. P. Only difference is set has changed. In fact, we are going to use the same way we did in the previous problem. Only difference is not this. This is the set. North is to the top of your page. South is to the bottom of your page. East is to the right of the page. West is to the left of the page. After that, you are going to apply right angle exam. If B is the question, I told you that first show direction of the magnetic force. Magnetic force is downward to the ground. Palm is the magnetic force. Correct? Show your palm in your page down. Now my palm is showing downward, correct? Correct?
Yes.
Alright, first step is okay. Next step. Look at the direction of the electric current. It is west, but my thumb is showing?
No.
This is wrong. My thumb must change direction. I am going to flip it until my thumb shows to west. Now my thumb is showing west. Palm is showing downward to the ground. So forefinger is
To the north.
to the north. Magnetic field is to the north in this question. So let's draw it. Magnetic field is to the north.
Teacher, how do we know the force is between the east and north?
Sorry?
How do we know the force is between the north and east?
We don't know. There's no between. Anybody can write it. It doesn't matter. It's just a drawing, okay? Now, we got the direction. Tell me what is the angle between electric current and magnetic field? 90. Yeah, the maximum magnetic force acts on it. Use the equation of the maximum magnetic force and calculate it. This is the equation for calculating magnetic force on a wire. BIL is F magnetic. Because F is given, I is given, L is given, B is unknown, I have to simplify I and L. Divide by I and L. So I and L will be simplified. B is equal to F magnetic divided by IL. F magnetic is 4 times 10 to the power negative 2. I is 22, L is 36. Use bracket for beginning and end of the denominator. So answer is 5 times 10 to the power negative 5 Tesla. This is magnitude. But what about direction? To the north. We are going to put a comma in here. North. No. In the third we don't have to the page. In the first set we have it. In the third set we have north, south, east, west, upward to the ground, down, upward to the sky, downward to the ground.
So why haven't there been any questions where we have to calculate a different angle, like sine?
Only one chapter question we have about the charged particles. Only one. When you meet them, you will see that. The others all are like this. Yeah. So we finished the magnetic force acting on a charge in a magnetic field. Magnetic force acting on a charge. Magnetic force acting on a current in a magnetic field. Okay? Did you get this one?
Yes.
All right. So now let's see what's next. Next one is the definition of the magnetic, definition of Tesla. Definition of Tesla. This statement is defining what one Tesla is. I mean, this definition is so important. Just in physics, everything is a definition. Tesla has also a definition. So we are going to. And it's up to you. Important or not. Okay. So if one coulomb charge is moving, of course, magnetic force exists. Only charge is in motion. If one coulomb charge moving at 1 meter per second perpendicular to magnetic field, and if this particle experiences a magnetic force of 1 Newton, then you can say that that magnetic field is 1 Tesla. Yeah, 1, 1, 1, 1. Every one of them is going to 1 in this equation. Yeah, F is 1 Newton, Q is 1 Coulomb, B is 1 meter per second. So then B is 1 Tesla. This is the definition of Tesla. But more than this is important. Equivalent of Tesla. Equivalent of Tesla. 1 Tesla can be written in different forms of the other units. So this is important in the perspective of 12th grade. We learned 2 equations about magnetic force. One equation is the magnetic force acting on a charged particle in a magnetic field, QVB. Second equation is the magnetic force acting on a wire, BIL. From these 2 equations, we can get equivalent unit of Tesla. Like what? Okay, in here, I'm going to leave B alone. How can I do that? If I divide both sides by QV and QV, Q's will simplify, V's will simplify, so B is equal to F divided by QV. Okay, F divided by QV. Now, I know that B is Tesla. But what is its equivalent? I'm going to choose this. What is unit of force? Newton. What is unit of electric charge? Coulomb. What is unit of speed? Meter per second. Then 1 Tesla is equal to what? 1 Newton divided by Coulomb multiplied by meter per second. This is one of the equivalent of Tesla. Second one is coming from second equation, which is the equation for magnetic force acting on a wire inside a magnetic field. Again, I'm going to leave B alone by simplifying I and L. Divide both sides by I and L. So, B is equal to M magnetic divided by IL. Okay? What is, again, B is Tesla. What is force unit? Newton. What is electric current unit? Ampere. What is the length unit? Meter. So 1 Tesla is equal to 1 Newton divided by ampere times meter. There is one more, but this is going to be explained much easier when we study chapter 6, section 1. One of them is this, but there's a long way if you know some information about the 11th grade, and I explained that at the beginning of the section 2, when I was talking about the uniform electric fields. Electric field can be calculated by 2 equations. One of them is delta V over D. I wrote it like this. Now, delta V is the potential difference between the plates. D is the distance between the plates. One equation is this, delta V over D. Second equation is force divided by charge, F over Q. I wrote both of them. So what does it mean? Electric field has 2 units again. One of them is volt per meter. Volt per meter. Second one is Newton per Coulomb. Both are the units of electric fields. I wrote them in the first page of your browser. At the same time, I explained them here. Now, looking in here, what is this? Newton per Coulomb, huh? So, Newton per Coulomb is equal to what? The volt per meter. Instead of Newton per Coulomb, I can insert volt per meter. I will do that. Now, instead of Newton per Coulomb, let me insert volt per meter. Let's do it. Newton changes to volt. Coulomb changes to meter. And multiply by meter per second. Okay? Then, you know, this must be flipped. Meter per second must be flipped. Second goes up in here, just near to the volt. It becomes volt times a second divided by meter times meter?
Meter squared.
Meter squared. Did we get that equation? Yes. One way is this, but in chapter 6, section 1, we are going to learn a very popular physics equation, which is electromagnetic induction, Faraday's law. After that equation, it will be much easier, this one. But until we learn that equation, this is the way how we convert, how we get this equation. Then 1 Tesla is equal to 1 volt times second divided by meter squared. These 3 can be ministry exam questions. They are asking this way. Which of the following is equal to Tesla? Which of the following is equal to Tesla? A. Newton divided by ampere times meter. Yes, it is equal to Tesla. B. Volt times second divided by meter squared. Yes, it is equal to Tesla. C. Newton divided by Coulomb times meter per second. Yes, it is equal to Tesla. Yani they can ask like this, which are equal to Tesla, which are not equal to Tesla. Such questions can be given to you, and it's given. The exam questions of this section, you will see that. Okay? Clear?